Syzygy episode 78, Muons broke my physics. And welcome back for another edition of the Syzygy podcast. It's been a little while. We've been on unforced hiatus. We didn't mean to. It's just one of those things kind of happened. Emily Brunsden sitting not across the other side of the world, but definitely across the other side of the Pennines from me. Emily, you're back in the country. How are you?
I have arrived back. Yes, I'm doing very well, thank you.
Excellent. Good. You're not looking particularly jet-lagged. When did you arrive back on our fair shores?
A few days ago, and no, I'm one of those horrible people that everybody hates, and I sleep quite well on aeroplanes, so I don't tend to have jet lag.
Do you think being an astronomer and getting used to doing crazy things with your body clock when you go observing and stuff, does that make it easier for you to absorb enormous shocks to the system like flying around the world? Do you reckon that's a thing?
It could be.
Have you done a poll, an unofficial poll of your fellow astronomers?
Well, most of my fellow astronomers are rubbish at sleeping on planes, so maybe that's not a very good data point.
I don't know. I'm not prepared to give up on this.
I'm just one of those people who moving vehicle sleep.
It's a good talent to have. That's a superpower, I reckon. I'm not prepared to give up on this. I think there's a thesis in this. I think we should investigate it, and I think we should get funding to do so. Welcome back, and I'm hoping that this heralds a new era for the Syzygy podcast, wherein we can get back into something vaguely approximating our normal podcast schedule again. I know listeners out there, we've been very quiet for a while, and we didn't want to. It just was kind of difficult to schedule into plans here and plans in New Zealand, where Emily's been catching up with friends and family, having a free life down there in New Zealand, where they are actually allowed to go and meet people and go to cafes and things. And now she's back, and we're able to do this Syzygy thing again, with any luck, regularly, like every week, every couple of weeks at most, rather than the sort of every month and a bit that we've been managing to so far. So welcome back. Today we're talking about a very, very exciting recent story in the world of astronomy, cosmology, and particle physics. So it's got you and me all over it, Emily, this one. This is all about the Muon G-2, yeah?
It's a wonderful way to start, isn't it? Let's talk about G-2. Hang on, wait a minute.
Can we just talk about G first? Yeah.
What's a G?
A muon?
What's a -2 doing in there?
Yeah. Well, look, we'll be getting to all of that in a second, but there's something that we really do need to touch on first, and that is the incredibly exciting news, which is we have a helicopter on another planet. Emily, this is so exciting.
It's brilliant. I mean, we keep breaking these records of, the longest controlled flight on another planet and all these kind of things. But I just love watching every video that we get. Every time there's a new little flight, and everything just seems to be working magically for our little Ginny.
It's all going so well. I thought, was there a little while there where there was some concern about whether or not it was actually going to be able to make the first flight? I didn't catch all of it, but I thought I saw a news article which said that the helicopter, what's it called? Ingenuity.
Ingenuity.
That it was having a few problems and it was having to go into sort of emergency charge-up mode or something. Did I get that right, or am I completely missing that?
Oh, I didn't catch that one, but I do remember a lot of talk about whether its blades were going to be big enough, basically, because Mars, very low atmosphere, low pressure, and you rely on that pressure to create buoyancy and lift. So although you can test things in similar pressure environments, I guess getting it out there and on the surface of the planet there's always that big scary thing of, will it really work in the real world?
Yeah, the difference between the models and the testing and the actual flying on another planet, there's a very big gulf there, particularly when you can't actually go with the helicopter to the other planet to check it out and do a couple of little test runs. No, this is the thing. And I loved the first images, or I guess you'd call it a video, but I think it was only probably about 4 frames long of an animated GIF. But it was the image from the rover looking out across at it. And there's the helicopter on the ground, and then there it is up in the air, and there it is back down on the ground again. So that's a flight. That happened. It worked. It was great. Such a wonderful moment. Really good.
And we've now seen, pictures that Perseverance has taken of Ginny, pictures that Ginny's taken of its shadow on the ground, and even just recently we saw some Mars Reconnaissance Orbiter images, which you can just pick out a little Perseverance on the ground as well. Really cute.
Yeah, it's fabulous. Fabulous stuff. Loving every minute of this new era of Mars exploration. It's great fun. One lovely thing that I was reading yesterday, which I hadn't really thought about, was that the first, powered flight on Mars lasted considerably longer than the first powered flight on Earth. When the Wright brothers did their plane back 100 and something years ago, that was like 12 seconds long. And Ingenuity's was how long? Like 30 seconds or something?
Yeah, something like that.
Blew it out of the water. The robots are absolutely killing it as far as the flight on a planet for the first time thing goes. So just loving it. Loving it. So well done, Ingenuity. Well done, Perseverance. Keep up the good work, and we'll report in as more fascinating things come to us from the Red Planet. So on to the business of today, Emily. We need to talk about a story which hit the interwebs and the papers and the television, the radio, and everywhere a couple of weeks ago, where it seemed like the entirety of the world of theoretical physics, and presumably astronomy, you can tell me about that in a minute, turned itself upside down and inside out over some new results that suggested that everything we know about how the universe works at its finest, most fundamental level of particle physics seems to be a bit broken. And this was very, very exciting. For everyone else in the world, they kind of went, what are you talking about? But the physicists were going nuts. And from my point of view, as someone who used to do research in theoretical particle physics, this is really, really cool. But what I'm really curious to know, Emily, is why we're talking about this on syzygy. The result that we're talking about is called the G-2, the Muon G-2 result. And it's about an esoteric fundamental particle called a muon. And it's about an even more esoteric measurement of a property of that muon called the anomalous magnetic moment. And it's really quite subtle and complicated. So what's that got to do with astronomy? Can you help fill in these gaps? Where are we starting here?
Yeah, I never imagined we'd have a syzygy episode called The Anomalous Magnetic Dipole Moment of a Muon.
I know.
That just doesn't sound like us, does it? It doesn't, I mean, there's no black holes, there's no galaxies, there's no stars.
It's a bit of an outlier. But that's okay. We'll go with it. We'll run with it.
It is a bit odd. But actually, what's really interesting is that all of these things actually, astronomy is just an application of physics, right? It's an physics applied to the real world, to the cosmos.
Well, as we like to say, everything's just an application of physics, Emily, but, carry on.
So when we talk about things like trying to understand the very, very basic structure of our universe, okay, we can go and look at things like the Big Bang, we can go and look at things like how the first stars form in the universe. But also really important is how do we understand things like how did our four fundamental forces of nature, the four things that govern all the physics that happens around us, how did they come about? And what are they all about?
Yeah, I mean, big questions, not the little questions. These are the big questions. Where did it all come from? And why is it all there? It's hard to get bigger than that, really.
Yeah, so we have the four fundamental forces in the universe, and these dictate all the other things that sort of happen. And that starts from the exciting things like the Big Bang all the way down to kind of how you and I are having this conversation over the internet.
Yeah, I mean, and at some point the real world kicks in and says, look, you can keep your particle physics, really classical mechanics, Newtonian stuff takes over, and, you can calculate things really easily using a much more simplified version of the laws of physics. But if you dig down enough, it's all about the quantum realm of particles and things. And so when you sort of drill into the way the universe operates, and particularly as you go back towards the Big Bang, when everything gets really, really hot and squeezed together, then astronomy, cosmology, and particle physics all become tied together and are one. And so anything that affects, at its deepest level what's going on in particle physics also affects at a very deep level what's going on in cosmology. But what's really interesting is it goes the other way as well, is that even though it's really hard to test some of the theories of theoretical physics here on the ground, on the Earth, because, you can only build a particle accelerator so big before it starts becoming farcical. The Large Hadron Collider is, however many miles across. It's about as big as we can do before we start, having to dig up entire countries in order to make one. But maybe you can turn around and say to the astronomers, Is there a way that we could test these things on a much larger scale in the universe at large? And that's where it gets really, really fun. So, Emily, what's a muon?
Muons. Muons are quite cute. I like muons. They're good. They're good characters. So we have kind of this zoo of different particles that we have in the universe, and we call these fundamental particles. They're particles that you break down the matter that we're made of, and you get to atoms. You break down atoms, you get things like protons and neutrons and electrons. Now, protons and neutrons you can break down further into quarks or quarks. But electrons, it turns out you can't break them down any further. That's it. That's kind of the end of the road. And
at least as far as we can tell, there's nothing inside an electron. It's its thing. Yeah.
Yeah. And so an electron is what we call a lepton. And a muon is a bit like an electron, except it's just a whole lot heavier.
Yeah, they're almost identical except for mass. And we don't know why. We don't know why muons exist. We had electrons and the world was quite fine with that. And then muons were discovered. And everyone went, what's that? What's that doing there? We don't need that. It's just like an electron, same charge, other properties almost identical. It's just really heavy.
Yeah, about 207 times heavier.
Yeah. And why? Because that's the way things seem to be ordered. So electron, a muon, and there's a third one, isn't there, which we discovered somewhat later on, can't remember exactly where, called a tau or a tauon, which is exactly the same as an electron and a muon, only heavier again, even bigger. So there's three of them, which is odd.
And it can be sort of easy to think, well, okay, electrons are around us all the time and they're quite important. Atoms, they're quite important things. Maybe muons aren't that important. But it turns out muons are really important, and they come from, I guess, if you were to sort of set up a little detector on your desk right now and say, let's find some muons. Well, you'd be in luck because you'd get something like 10,000 muons per meter squared coming from the atmosphere. John Earth.
10,000 per meter squared. That's a lot. I knew that they were coming down. I just didn't know there were that many of them.
Per minute.
So where are they coming from in the atmosphere? Why is that happening?
So we get them because cosmic rays come in from space. So cosmic rays, really, really high energy particles coming from space, coming into the atmosphere, colliding with particles in the atmosphere, and then they create these muons.
Right.
And muons, they don't hang around for long.
Yeah, that's right. Because they're almost exactly the same as electrons, but really, really heavy. And so that extra mass, which, as we know from Einstein and colleagues, energy is mass is energy. You can turn mass into energy. And so if there are lighter things than the muon that the muon could, fall apart, decay into, then it will. And the muon tends to do that really, really fast. Do we have a number on that?
Yeah, it's about 2.2 microseconds.
Right, which is
the lifetime of a muon.
2.2 millionths of a second, which is not very long.
It sounds not very long. I guess in particle physics world, though, I think it's actually quite long. I mean, if you're trying to detect things that only exist for very, very tiny fractions of a second at things like the Large Hadron Collider at CERN, you'd love to have things hang around for a few microseconds. That would be easy.
Well, there is that, yeah. The kind of stuff that they're looking at CERN. I mean, some of the, when they bash stuff together at CERN, some of the particles that come flinging out of that last for really long periods of time. But some of the really interesting ones, like, for example, the Higgs boson, sticks around for ludicrously short fractions of a second. So the muon, you're right, by comparison, is quite long-lived. But the interesting part about the whole, you can detect them on your desk if you've got the right kind of detector, they're raining down from the atmosphere, is that by sort of old-style classical calculations, that tiny fraction of a second that the muons stick around for is not enough time for them to reach the ground from their creation up there in the atmosphere. But they do, and they do for a really, really interesting physical reason. And I'm going to leave that pause there to see whether or not you're going to throw in what that is.
I don't remember. This is something I remember. You've just triggered a memory of particle physics when I was in...
It's because of relativity, Einstein's relativity, right? The faster you go, the more time and space go a little bit weird, right? And so when you're traveling really, really fast with respect to the ground, the distance from where you were created as a muon up there in the clouds down to the ground becomes much, much shorter. It's what's known as length contraction, relativistic length contraction. And so the muon sees a much shorter distance down to the ground. It can cover it in that fraction of a second. Conversely, seeing it from our viewpoint standing on the ground, the time, if the muon had a little watch on, then we would see the time in the muon's frame of reference, the time as is passing for the muon, to be going much, much slower. That's what's known as time dilation. Time travels more slowly for something that's moving really quickly relative to you. And so, yeah, the muon only lasts a tiny fraction of a second, but in its reference frame, that tiny fraction of a second lasts long enough for it to actually make it down to the ground. It's really, really cool. It shouldn't get there, but Einstein's relativity says it does, and we can detect them at the ground, which makes it a really nice test and example of relativity physics. But it also means that, back when these things were discovered, we were able to detect them in large quantities down here on the ground using the right kind of detectors, because stuff's bashing into other stuff up in the atmosphere and creating them in vast quantities.
Absolutely. And similarly, the other context I think we might have mentioned muons in before in this podcast is when we talk about neutrinos. Muons are really, really important for creating the neutrinos that we try and observe deep, deep underground, whether that's in underground caverns filled with water or even under the Antarctic ice shelves, about a kilometre deep as ice cube. And what they're looking for is muons travelling at, again, these extraordinary speeds, colliding with particles in the ice and then generating neutrinos, these short-lived, extra exciting particles.
Yes, because there's sort of... The interactions, the forces that allow an electron or a muon or a tau to be created when stuff bashes together and you turn some of that energy into new stuff. If you create an electron or a muon or a tau, you will also create along the way a neutrino. That's just how the universe works. And so in those bashing together interactions, whenever you get a muon, you'll also get a particular kind of neutrino, which you can then go on to try to detect elsewhere.
Yeah. So what we're talking about in terms of the property of a muon that makes it so interesting today is that it's got a magnetic dipole moment. Now, that property in itself is not that, it is interesting, but it's not that different to what other particles have. All particles have a magnetic dipole moment, right?
Yeah.
And this is kind of a property that gets really weird when you look at it at the small fundamental level, but it's actually pretty normal when you look at it at the macro scale or at normal human scales. Effectively, if you get enough bits that have a magnetic dipole moment and you stick them together, then you get like a bar magnet, which is kind of nice.
Exactly. So a magnetic moment, you can think of it a little bit like a tiny little bar magnet, pointing in a direction in space, right? Now, why would a particle like a muon or an electron or a proton have a little bar magnet associated with it? Well, it's a little bit like the fact that when you have an electric current flowing in a wire, you get a magnetic field around that wire, right? And this is something that James Clerk Maxwell sort of tied all of the theories of electricity and magnetism together back 100 and something years ago, back in the 19th century, right? Put all this together and said, if you've got electricity flowing, you get a magnetic field. Magnetic fields and electric fields are all tied together. And so if you have a little loop of electric current going around in a circle, then you'll get a magnetic field going through the middle of that circle. And so it's a little jump from there to if you've got a little ball of charge spinning around, then that's a spinning bit of charge, and so you'll get a magnetic field associated with that. So it's like a tiny little bar magnet pointing with a north and a south. And so if you look at something like an electron or a muon, which is a tiny little, you can think of it as a sphere of charge or a dot of charge, then if that's spinning around, then it will have a little magnetic moment, a little bar magnety thing associated with it. The trouble is, you can't really think of the electron or the muon as a little ball of charge spinning around. But that gets very complicated and subtle. You can think of it as if it were that way. There's a property of these particles which is known as spin. And it's called spin because it's like they're spinning around. They're not, but it's kind of like they are. And so because they have spin and because they have charge, they have a magnetic moment, which we call G, because G for magnetic moment, I don't know. You tell me. I guess the theoretical physicists are just as good at naming things as the astronomers are, I guess.
Yeah, and this G comes from what we love and love to hate, I guess. Well, I love to hate it, but maybe you love to love it. The Standard Model of Particle Physics.
Yes. All right. So shall we unpack that one a little bit then? The Standard Model, which is that's a bad name. It's another bad name of.
It's a very
theoretical
naughty
physics.
name.
I mean, it's a bit silly because for starters, it's not one model, right? It's a bunch of things bolted together. But the Standard Model of Particle Physics is our best yet collection of theories about the way matter and energy interact through the electromagnetic force, or the what's known as QED, quantum electrodynamics, through the strong nuclear force, which is a thing that sticks all the quarks together inside protons and neutrons, and it sticks them together with other particles called gluons, which is very cool. You've got the weak nuclear force, which is the one that is involved in certain kinds of nuclear decays, and it's where, for example, a proton can turn into a neutron by emitting an anti-electron and a neutrino. So one of the quarks inside the proton will turn into a completely different kind of particle and another completely different kind of particle. And it's through this, what's known as the weak nuclear force, that interaction happens. And in the Standard Model there, what else have we got?
Well, the Standard Model does sort of say that there's four forces, although it doesn't really kind of work that well with the fourth force.
Yeah. So we've had, hang on.
You're glossing over a little bit here.
Electromagnetism, we've had strong nuclear force, we have weak nuclear force, and then the fourth of the four forces, which is the one that we've missed out, Emily?
Gravity.
It's one of the big ones.
Well, that's the thing. Is it the big one?
Well, no, it's not the big one. I guess at a quantum level, it's really not, is it?
It's a tiny one.
It's tiny. I mean, it's big on our scale.
It's wonderful.
Like, of all the forces that we notice around us, there's two really big ones, one of which you're probably more familiar with just in your day-to-day experience. Gravity, you're very familiar with. If you get up and you trip over, you're going to fall over, smash your face on the ground because gravity, right? That's how that happens. But the pain that you feel in your face when you hit the ground, that's actually electromagnetism, right? That's all the charges in the atoms in the ground interacting with the charges in the atoms in your face and pushing against each other really hard when they get really close. And that's where the pain comes from. So you may not have thought of it that way, but smacking your head on the ground is electromagnetism. The falling towards the ground is gravity. Trouble is, when you look down at the really, really, really small, fine, minute world of quantum physics, gravity is ludicrously weak at those levels. The other forces are much, 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 much stronger by, like, I can't remember how many orders of magnitude, but it is an extraordinary amount.
10 to the 38.
There you go. Emily's
from
got
the strong force to gravity, 10 to the 38.
Now that's, for those who are following along at home, a 1 followed by 38 zeros, that the strong force is stronger than the gravitational force at the level of particles. And so, to all intents and purposes, gravity is literally negligible. It's just not there, right? Particles don't fall under the influence of gravity. It just, before something else happens to them. And so in the Standard Model, we do have gravity. It's just kind of pushed to the side and then there's this thing which we know is there, but we don't yet have a quantum theory of gravity. We don't know how gravity applies in the quantum world. And on one hand, that's fine because it's so small it doesn't really matter anyway. But on the other hand, it's really not fine because, unfortunately, at a mathematical level, general relativity, which is the best theory we've got of gravity, thank you, Albert Einstein and colleagues, is incompatible with, does not work, breaks quantum theory, which explains everything else. They can't both be true. And there's a problem there.
And this is why I'm not well. I mean, I can't say whether or not you're a fan. I mean, it describes the physics that we have around it. But this is one of the reasons why I guess the Standard Model of Particle Physics bugs me, because it's brilliant. It's got these four forces. It describes wonderfully. It describes. I think it's got 17 elementary particles that it describes. It's all great. You can describe everything that's going on in sort of our day-to-day lives. Loads of things on the quantum level, but. And this is a pretty big but.
It is. A really big bug.
I wrote down a little list of the things that it doesn't explain.
Go on then.
So you've got your general relativity, which you've just mentioned.
Which is a big one. I mean, if you're talking about the two paradigms of the 20th century physics, which changed everything, it was quantum, which has done really well, and it's general relativity, which has done really well. You can't just leave one of them out or say, well, it doesn't matter that they don't work. No, this is a fundamental problem. So that's a big one.
Okay, so it doesn't explain general relativity. It doesn't explain why neutrinos oscillate between different flavors.
No.
So effectively changing types of neutrinos, which is quite important in quantum scale. Okay, it doesn't really matter to you and me sitting having this conversation, but it's kind of important.
It's a very, very big one. That was all kind of happening around the time I was doing my PhD in the late 90s, early 2000s, when there was a thing called the solar neutrino problem, where there were a lot of neutrinos coming out of the sun, and we could detect a bunch of them, even though they're really, really hard to detect. There are a lot of them, so we could see them. But there weren't nearly as many as there ought to be.
There was almost exactly a third of what we were predicting from theory, which was a suspicious number.
Yeah. Because if it had been like, a seventh or something, that's a bit odd. Maybe that's just a number. But a third, because we did know that there are actually 3 different kinds of neutrino. Because there's one that goes with the electron, and one that goes with the muon, and one that goes with the tau. And they're different things. And so if all of the electron neutrinos coming out of the sun, only 1/3 of them turn up at Earth, maybe the other 2/3 turned into the other kinds along the way. And it turns out that's what happened, but the standard model doesn't explain that. We know it happened, we just don't know why. Big hole, bit of a problem.
So that matters to you and I, but maybe not to everybody. But there are some other things that maybe more people should also worry about. One of them is baryon asymmetry. This is a scary one. This is basically, why is there matter in the universe over antimatter? Why are we all made out of matter, and there's so much matter everywhere? And in theory, if you take standard model particle physics, there should be as much antimatter as matter, and we should have all annihilated, and that's it.
It's a really subtle problem, right? Like, we look around us and we go, well, there's this stuff, but the more you learn about how particle physics works, the more you learn that antimatter, which sounds like something from Star Trek, but is very, very real, is exactly the same as matter. It's just sort of, I was about to say a mirror image, but that's not quite the right analogy.
Well, we've got electrons and positrons are great examples. They're very familiar to us.
Yeah, and we can make these routinely all the time in particle accelerators and stuff in the lab. Like, it's real. You can make an atom of anti-hydrogen with an anti-electron going around an anti-proton. It doesn't last very long, but you can do it. The question is, if the laws of the universe are completely symmetric with respect to matter and antimatter, they treat them exactly the same, then why are we here? Because there should have been exactly the same amount made in the beginning, which would then all have annihilated again, because when an electron meets an anti-electron, they annihilate to just form energy, photons. Same's true of all the other particles and their antiparticles. So why is there anything left? Why is everything that we see in the universe matter and not just a roiling and slowly cooling amount of energy with everything gone? So we don't know. We don't have an answer for that. We don't have an answer for why we're here, which is, fundamental question, one of the big ones.
It's up there. But, if you want to add some more big questions to your things that standard model can't explain, we've got dark matter.
Yeah, very little ideas still on that one. So dark matter, remind us, Emily, what's the dark matter conundrum?
So dark matter is a form of matter that we can detect out there in the universe, and we can detect its gravitational presence. We can detect it in galaxies. We can detect it in clusters of galaxies. We know it's there because it happens to make galaxies rotate at a particular speed. It makes galaxies on very large scales move relatively quickly with respect to one another. We can see it in terms of its gravitational effect, but it has no interaction with photons or electromagnetism. So we can't see it. It's a problem. It's matter that we can't see.
We know it's there. We can see its influence. And all of that influence that we see is gravitational, isn't it?
Exactly.
So as we mentioned before, because gravity is on a physics scale, on a particle physics scale, is incredibly weak, if you're seeing large-scale influences of gravity over the scale of galaxies and clusters of galaxies and superclusters of galaxies, then there's got to be a lot of dark matter around. This is not just a little dusting of it. There's got to be quite a lot there, right?
Oh, yeah, orders of magnitude more than we have of our ordinary matter that we have here,
Right.
Everyday lives.
More than the stuff we see is the stuff that we don't see. And the standard model says, don't know, and just shrugs its shoulders. I've got nothing. There's nothing that we've got in everything that we can see in our models, in our theories, that can explain that. So, yeah, bit of a problem.
And do you want the last one, just, to round off your...
Sure, go on. I mean, we're already
list.
feeling a little bit depressed about the state of modern physics, but go on, yeah.
Yeah, can you also please sort out dark energy? Okay, thanks.
So when you said a second ago that, in the universe, in terms of total amount of stuff, you've got the stuff we can see, and that makes up, what's the current estimate?
4 to 5%.
4 to 5% of the known stuff in the universe. And then there's the dark matter, which is about another 20, 25%. Is that
Yep.
right? And so everything else, let's call it in the order of 70+% of everything is dark energy. And we don't know what that is. Emily, what's the dark energy doing? How do we know it's there?
It's accelerating the expansion of the universe. So galaxies, very, very distant galaxies, are moving away from us faster and faster and faster. So there's some force that's pushing them, some energy that's pushing them to accelerate them away from us. And yeah, we have no idea much beyond that.
Yeah, again, you look through the ledger of all the stuff that's in the standard model, all of these great theories that we rely on every day to do real things in the world, and they work, and it's got nothing. It's, I don't know, just shrugs again and says, dark energy, nothing. Literally nothing to explain that.
Yep. So there's my shopping list for particle physics.
Good.
Can you please carry on?
You've made a very strong case. But I mean, slightly less facetiously, this is the stuff that makes physicists really, really excited, right? Because if we had all the answers, if we could just point to this bit over here in the standard model and go, the dark matter's just that. It's just the neutrinos being silly, then problem solved. And if we could point to this other bit and say, no, it's just the Higgs boson gives us dark energy, it's fine, it's all good, then it'd be really boring because it'd be so little to do. It would be just sort of, polishing things off and getting the next decimal place, and it'd be really kind of dull. This is where the exciting stuff is all of those open questions that you just listed are where people are doing the exciting work now in theoretical physics and cosmology and astronomy to be able to say, we don't get it. It is broken. What's going on? And that's the fun part.
Exactly. And it's exactly experiments like the one we're talking about today, which are contributing to that.
We get there eventually.
We'll get
That's
there.
absolutely right. Yeah. So, bringing it right around then, we've talked a little bit about what a muon is. It's like the electron, only heavier. We see them in cosmic ray showers where these really energetic cosmic rays from elsewhere in the universe bash into our atmosphere and make muons, which rain down on the surface, and thanks to Einsteinian relativity, are actually able to make it to the surface where we can detect them, which is cool. And we've talked very briefly about the fact that they have a property called their magnetic moment, which is you can think of as, because they're charged and because they're kind of a bit like spinning little balls, then they have their own little magnetic field, their own little bar magnet associated with them. Great. So what?
So we take our model, our lovely standard model of particle physics, and we calculate what that magnetic moment should be. And yeah, I mean, you can paraphrase numbers into different ways, and the way that I guess that's quite nice, I think, that we do this in particle physics is we kind of turn the numbers around and we make this magnetic moment to be equal to 2.
Yeah. I mean, to all intents and purposes, if you do the first calculation of this, because it's very, very complicated calculations, and these are sorts of things when you do a bit of theoretical physics, your brain starts breaking a bit at how quickly things get really complicated when you're calculating with particles. But the first simplest calculation you can do, the answer's 2. Why is it 2? I don't know. It just is.
It's just 2.
We could divide it by 2, call it 1 if you want, but it's 2. But things aren't that simple because you then add in a couple of little corrections. Oh, but what if we think about this little bit? And then there's this little bit that contributes a little bit more, but then it subtracts a little bit. And you get 2 and a little bit, or 2 minus a little bit. And so the anomalous magnetic moment is the G minus 2 bit. It's where how much does the actual number differ from that first, broad brush? It ought to be about 2. Yeah, okay. How much does it differ from that? And that's what's known as the anomalous magnetic moment. It's a measure of how strongly do all of the tiny little effects of the quantum theories influence these calculations.
Absolutely. And this is something that we can now, or have been doing for some time, trying to measure in the laboratory as well. To check our theory, we can do the measurement as well.
That's right. So you can compare the measurement against the theory. And, just to be absolutely clear, this is one of, if not the best measurements and theoretical calculations we've ever been able to do in the history of physics. The one that you do for the electron's anomalous magnetic moment, you can measure it in the lab to, I'm just counting it on the screen now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures. It agrees with experiment. So you measure it, and then you do the calculation, and it's an incredibly long calculation, really, 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 really hard. But when you do that, you get an accuracy better than 1 part in a billion. And that's off the charts. Like that, I think, as far as I know, that beats any other experimental and theoretical calculation on the planet. So it works. It's really, really good. When you do the same thing for a muon, it's a bit harder to measure and it's a bit harder to calculate. And so you don't get quite that degree of accuracy, but you still get pretty good.
Absolutely. And so it's the experimental results that came out earlier this month that are the ones that everyone's getting quite excited about, because it turned out that in 2001, we did some first kind of tests and measurements. And this is what they call the Muon G-2 collaboration, who have been working in Fermilab in Illinois. And what they've got is they've got a 15-meter ring. It's got a giant magnetic field. And they send muons around this magnetic field. And the muons, of course, have their own magnetic moment. They're interacting with this magnetic field and this ring. And so they kind of wobble as they go around. And so they're wobbling, wobbling, wobbling. And you can measure that wobble, and you use that to therefore measure the muons' magnetic moment.
Can I just pause and duck in here for a moment to say, isn't it fabulous that there are entire teams of really, really highly professional and well-respected physicists in the world who are doing research, and their entire team is named after the research, where they're basically looking at the infinitesimal wobble of an esoteric particle around a large magnetic ring. What a weird job. Don't you think? Anyway,
well, I find all particle physics is weird, but maybe I shouldn't go on down that line too much.
No, you're absolutely right. It is true.
And so this experiment, there were some hints when they first tried this experiment back in 2001 that maybe the numbers coming out weren't meeting up very well with the theoretical numbers, but it was kind of like a first try. Okay, well, maybe there were some bits of the experiment that didn't quite work.
That sort of thing happens all the time, and people get excited, and then the discrepancy goes away when you think, oh, that's right, we forgot about this thing. Yeah, that's okay. It's all good now.
And what I love about the way they set up this experiment is they said, right, okay, this is really important. We've got to get this right. So we're going to do this experiment, and we're going to do it blind, meaning we can't possibly have any human bias in the interpretation or the construction of the results that could say, that we've actually influenced those the way that those numbers have been produced. So I've never sort of come across this in quite such a dramatic way, but they created a blind test.
How did they do that?
So when they were measuring the magnetic moments, what they're doing is they're measuring a frequency. Mm-hmm. And the way that you measure that frequency is you've got to have a clock, right?
Right.
And so what they did was that they actually took the information from the timing of the clock, and they put it in a sealed envelope, and nobody in the actual experimental collaboration knew the timing of the clock. They put it actually in a physical sealed envelope, gave it to some kind of friends and collaborators who weren't anywhere near the experiment, not involved whatsoever. This is the brilliant thing. Then they did all their work. They had no idea what the actual timings were. They sort of, they didn't have that data to kind of make a final result from. And then they all got together I think it was in March, and they all got together on Zoom, about 200 people on Zoom, and they had this dramatic moment where the person who was looking after the envelope opened up the envelope and told them the frequency to input.
That's brilliant. And so they could then say, okay, hang on, give me a sec. Oh my God, that's the result. That's hilarious.
It's awesome, isn't it? It's like the Academy Awards of particle physics.
So no wonder this result has had such, so many of the reports about this have had this breathless sense of the world of theoretical physics is so excited about this. No wonder they had that built in from the start, is that when we learn this result, it's going to be at the end point of a really, really tense period where we don't know what's happening. We're literally working in the dark with these calculations. I think that's brilliant. That's so cool.
It's nice, isn't it? It's really good.
But the punchline, of course, is the number that they got. So how did it turn out?
So it's about 4.2 sigma away from the theoretical number. So 4.2 sigma is four and a bit times the standard deviation. Now that's quite different. It's what we normally take as kind of our absolute gold standard of being this is a true measurement, is 5 sigma. So we're nearly there.
So it's tantalizing. Now, just unpacking that a little bit. So if you're not familiar with the whole, what's a sigma? What's a standard deviation? If you think of your classic bell curve shape, right? It's big and tall in the middle. So thinking about, for example, people's height, right? Most people are going to be around the average height, and so there's a large number of people collected in this distribution in the middle. And then you're going to have a bunch of people who are much, much shorter than average height, and so they're down in one tail of this bell shape. And then there are some incredibly tall people who are up in the other tail of the bell shape, but most people are clustered around the middle of the bell, right? So that's our bell curve. And the standard deviation measures how wide the curve is, right? So over what range of heights in that case, or physics results in the case of the G-2, over what range do they fall? So the standard deviation measures how far out into the tail are you going. And so one standard deviation between one either side of the mean, so you've gone out one standard deviation, that captures, off the top of my head, is that around about 60% or something?
I think it's 68% maybe?
60, something like that. Roughly 2/3 of
most
everyone in the sample are within one sigma, one standard deviation either side. Get out to 2 and you're up into around about 90%. Out to 3 and you're up into the high 90s. So out to 4 sigma, 4 standard deviations either side, you're well up into the 1 in 1,000, 1 in 10,000 chance that you could be out here purely by chance. 5 sigma, being the gold standard of physics, says we want to be sure. And so when you're getting right out into those tails, what you're basically saying is, if we expected that there is no result, that the experiment and the theory completely agree, sitting right there in the middle of the bell curve, at no sigma away from the mean, but just by pure coincidence, we might accidentally measure something which is a long way away from that. And so what's the chance of us measuring something which is 5 sigma away? And it's very, very, very small. The chances of that happening purely by coincidence is 1 in
a large number,
several million. It's got to be.
It's quite high, yeah.
And so you're really confident that that's not random chance, that there's something real there. 4.2 sigma is almost there. It's really, really unlikely. Part of the problem, though, Emily, is that 4.2 or 4 standard deviation results do come and go. Particle physicists who are sifting through huge amounts of data at the Large Hadron Collider and things like that will see a little bump appear in their results and go, oh, there's something interesting. Oh my goodness, it's 2 sigma. Oh, we gather more data and say, oh, it's 3 sigma now. This is something real, but you can't yet. And then it's 3.5, and then you get more and more data, and the bump goes away, and more stats build up, and you go, no, that was just random chance. It's gone now. So 4.2 standard deviations is tantalizing. Is this real or not? But we still don't have an answer.
Yeah. It's high enough to get excited, but not so high that you can be sure.
Exactly. So what is the thing? Let's say for the sake of an argument that it is real. What are we seeing here? The fact that the experiment and the theory differ, what does that mean? What's that telling us?
So there's two sort of ways you can sort of go ahead and think about it, and maybe both are actually quite useful. So you can think about it either as you've got an extra sort of force which is happening here, which is causing the muons to kind of wiggle about, or you've got some extra what we call virtual particles which are coming in and disrupting the muon.
Yes, I mean, something, if they are different, if the experiment and the theory are different, something's got to be causing that difference. And it's not within the standard model because we use the standard model to make the calculation. So it's something new. And what you're saying is it could be new force, by which we mean a new kind of interaction, a new something on the same level as the strong and the weak nuclear forces and electromagnetism and, God help us, gravity. Or some other kind of new particle that we haven't accounted for yet. Or something.
Or both. Well, maybe a particle associated
Yeah.
with a force, right? And these things do pair up.
And that's the exciting part, because if it's something new, then the physicists get to go and play some more and come up with ideas for what could it be. Let's play with some theories, which is really, really cool.
Exactly, and I love the way that these things are sort of coming around. So one particle, I guess, which is one of the contenders, which it doesn't have a huge following. It's it's a particle that had its heyday.
Makes it sound like an Instagram influencer or something.
Yeah, it's not great on Instagram.
It's very popular back in the 90s.
Well, actually, sort of more even further back, if you go back into the sort of 70s, actually, this group of particles were quite popular, and those are supersymmetric particles or superparticles.
Yes, SUSY, as it's known, supersymmetry, which is, it's an idea which is still around. And I think most theoretical physicists who work in the field reckon that supersymmetry is probably going to be, like, when we do eventually figure out what is beyond the standard model, because there's got to be something, because as you said before, the standard model has so many things it can't do. When we do eventually figure out what is past the standard model, supersymmetry is probably going to be in there somewhere. So what is supersymmetry? All of the particles that we know, the electron, the quarks, there's 6 different quarks, and there's the neutrinos, and there's the force-carrying particles like the photon and things like that, would all have another partner particle, its supersymmetric particle, that is its counterpoint in this greater theory of particle physics. We haven't found any of those other particles yet. And there would be a lot of them, because there's, what did you say before, 17 particles that we know of, which means that there would be at least another 17 that we haven't yet seen, all the supersymmetric particles. But that they would, for whatever reason, be considerably heavier than any of the ones that we've seen so far, which is why we haven't found them yet. They're really hard to produce in particle accelerators and stuff. So the idea would be that we've only seen one aspect of the particle world. There's this other supersymmetric side that we haven't found yet, but that would help us to explain a whole bunch of stuff in particle physics. So it could be them, maybe, supersymmetry?
Yeah. I mean, we've tried really, really hard to find these particles. I mean, we haven't just sort of said, oh, yeah, they might be just a bit heavier. We'll catch up with them at some point. No, we've really, really tried. Like things like the Large Hadron Collider have looked very diligently for these heavy particles, and they've actually got boundaries of sort of ranges of mass where they know that they're not there, because hey guys, we've checked.
Would have seen them.
Yeah, we would have seen them by now.
Yeah. Although, very interestingly, I was having a chat with a guy that I know who's a theoretical physicist down in Adelaide in Australia, but does a lot of work at the LHC. But his thing is trawling through data. And the thing about particle physics is it's a bit like astronomy. There is so much data that you could spend your entire career just looking back at what we've already collected and sifting through it. And his thing is, he and a bunch of his colleagues, he's by no means alone on this, his thing is we could already have found these things. We just haven't spotted them yet in the data. Because when you look through the data that comes out of something like the Large Hadron Collider, you are looking very, very specifically for very, very specific things. And all the other data you just sort of just throw away. You go and put it in a cupboard. And he said, all that stuff that you have not looked at could really, really easily have loads of important signals in them that we have just never looked because that wasn't what we were looking for. So it's a fascinating idea that yeah, maybe it's not in the LHC data. Maybe the LHC isn't big enough for us to find these things, but maybe they are there. Maybe it's there, which is a tantalizing idea.
Exactly, yeah. And people who do really love supersymmetry also you can join the dots and say, well, if there's these heavy particles out there that we haven't found, well, hey, maybe that's something to do with dark matter as well.
Could be, which would be nice, because if you're looking for something which are really, really hard to interact with, and we know that they must be because we've never seen one, but is also really, really massive, we know it has to be because that's the whole point of dark matter, then that would be a really nice candidate. That would be cool.
Yeah. I mean, it's a little bit tricky because it turns out with just your sort of very off-the-shelf supersymmetric theory, it turns out you end up with way too much dark matter in your universe. But
everything collapses down and we all get destroyed. So, yeah. But the thing about these theories is because it is beyond the standard model, everyone and their dog has got their own version of a supersymmetric extension to the standard model. There are so many different kinds. And without data, without real-world experimental data to go from, there's no way to choose between them other than, well, I think it should be this and I've got the following reasons. So we need the data. And this is where the astronomers are going to come in, Emily. We need astronomical, cosmological data to start pointing the theory in the right direction to say, let's start whittling this down. It can't be that because we know that on a large scale, the universe looks like this. And your theory would ruin that. So throw it out. Can't work.
Exactly. And, it may not be that supersymmetry is the answer to this. There are other particles. Everyone's, as you say, everyone in particle physics has got their favourite theories.
Yeah. Other particles
are available. Yep. Leptoquarks.
I've heard of leptoquarks. I can't remember what a leptoquark is.
A leptoquark can transform a quark to a lepton.
I have to think about that one. How does that work?
I don't know.
Isn't that what they do in the weak? It must be different to the weak nuclear force. Leptoquarks. I'm going to have to go and look that one up.
Yep, leptoquarks.
Very cool. I'm looking them up on Wikipedia right now, and they're hypothetical particles that would interact with quarks and leptons. They're color triplet bosons that carry both lepton and baryon numbers. Which, if you don't know what that means, trust me, it's very, very cool. So, okay, could be leptoquarks.
Do I have to send an apology to your family for destroying their weekend with you because you're now going to be spending hours trawling through particle physics textbooks?
Yeah, sorry everyone. My kids are going to hate me for this one. No, kids, seriously, leptoquarks, they're great. And so, sorry, what was the other one? The
Z prime boson.
So what's a Z prime boson? Okay, I'm going to have to look this one up now.
Okay, yeah, so Z bosons are sort of run-of-your-mill bosons that we have for the strong nuclear force. So there's something that particle physicists are very familiar with.
Yep.
And Z prime bosons are kind of similar to those, but Z bosons work with the weak force, not the strong force. But they're similar to that. They're just somehow a little bit different. I didn't write down why they won't be a little bit different, but they're just a bit.
But they just are.
When you get to 17 particles, come on.
Yeah, you start losing track. You start running out of letters for a start and alphabets. You go through the English, you go through the Greek alphabet, you start just completely running out of alphabets entirely. Yeah.
But what I can give actually particle physicists ultimate credit for is at least some of the names. Some of the names for the particles are great, but some of the names for the forces that these particles or these other forces that might be causing this anomaly are. Because I just love these. So we've got B minus L2. That's a force.
I mean, B minus L2 could be like a supernova remnant off on the other side of the galaxy. It's got that kind of flavor to it it's just a bunch of letters and numbers. It doesn't mean anything.
What about the flavor force?
Flavor force, though. I like flavor force. Yeah, when you get down into things like quarks, down in the inside protons and neutrons, right? Each of those quarks has a charge, like an electric charge, except that it's not an electric charge, or rather, they have an electric charge, but they also have a different kind of charge, which we call a color charge. And so you talk about red, green, and blue quarks. But they also have a flavor, and that is the type of quark they are. So they're a 6 different flavors of quarks. There's up quarks and down quarks and strange quarks and charm quarks, and my favorites, which used to be called truth and beauty quarks, but then got changed to top and bottom quarks because I think everyone found like, no, this is getting a little bit too much. We're getting a bit too cute with this one, a bit too whimsical. Pull it back, top and bottom rather than truth and beauty. So that's flavor.
That's a flavor force.
Flavor, and there's a flavor force. Interesting.
And my absolute favorite, I don't really care what the science is behind this one now. We've just got to adopt it. It's the third family hyperforce.
Oh, third family hyperforce. I mean, hyperforce is one thing, but third family hyperforce. So I haven't heard of that one, but third family, third generation, I wonder if that's related to the fact that, okay, so we talked before about that there's electrons, muons, and tauons, tau particles. There are 3, if you like, generations of electron. I just mentioned the 6 quarks that you get. There's the up and down quark, which make up protons and neutrons. But the up and down have their heavier siblings, which are the strange and charm quarks. So that's generation 2. Or maybe family 2. I don't know if family and generation are the same thing. And then generation 3 are the truth and beauty or top and bottom quarks. And as far as we know, that's where it stops. Why do you get 3 generations? Why do you get 3 generations of electrony things? Why do you get 3 generations of quarky things? It's all very deep and very troubling, Emily, and we still don't have answers to that.
I'm still just working with hyperforce. That's great.
Hyperforce. Yeah, it's good stuff.
I wish I could name something a hyperforce.
Well, I think you should. I think your next paper, you should just, unilaterally go out and name something with hyper. But I guess the bottom line, Emily, is this, right? If we come around to where are we at with all of this excitement, we've found a couple of things here. One is that physics may well be broken, or at least we know it is broken because it's inconsistent and it's incomplete. So, there's something there's going to have to go. But maybe we finally found evidence for the fact that it really is broken with the muons anomalous magnetic moment, right? We're seeing this discrepancy. And so where do you go from there? Well, maybe it's this third family hyperforce. Maybe it's, Z prime boson. Who knows? Maybe it's supersymmetry. There's all sorts of places you can go. Loads of theories, and it's really exciting. But the flip side to that coin is maybe the discrepancy between experiment and theory isn't actually there. And not long after all of these results were reported breathlessly in the press all over the world, a bunch of other theorists started quietly raising their hand and clearing their throats and saying, or not, And this is very close to my heart because the area that I did my PhD in, where I used to do research back in the day, was in an area which was known as lattice quantum chromodynamics. And if we pull that apart, quantum chromodynamics is the theory of quarks. It's the color theory. It's the color charge, how quarks stick together to make protons and neutrons, that kind of thing. It's the strong force, right? Lattice quantum chromodynamics is because normal QCD is really, really, really hard mathematically. You can't calculate with it the same way that you can calculate about atoms with electromagnetism and write down the equations and do calculations and get numbers out the end. You can't do that with quarks because the maths is different and it's really, really hard. But what you can do is you can simulate all this stuff on a computer. You can make a tiny little baby universe, which is only 10 steps wide and 10 steps long and 10 steps deep and 10 steps in time. And you can stick a couple of mathematical objects in it called quarks and see what they do. And if they stick together, you've made a proton. And that's a way of dealing with a mathematically difficult theory, and it's known as lattice QCD. And you can do a bunch of these calculations. And it's a way of doing calculations, real calculations, without actually having to do the equations yourself. You just let the computer churn it out. And lattice calculations of the muons G-2 suggest that the previous calculations that they'd done were wrong by a small but significant amount in a way which brings it much closer to the experimental result. In other words, the lattice people, the people who are doing the supercomputer calculations, are going, yeah, I think the theory does actually agree with experiment, maybe. In which case, all of this hoo-ha would just slowly disappear into the sunset. The 4.2 sigma is a 4.2 sigma based on a flawed calculation. And that would be really disappointing for everyone involved. So I guess the lesson there maybe, Emily, is, I don't know, watch this space. We'll find out. I think probably in the next couple of months we might hear more about this.
Absolutely. And I don't think it's quite as disappointing as all that. I mean, sometimes it's nice when your cozy, cuddly, friendly standard model turns out to be right once again. I mean, we've talked several times about how we've made more and more extraordinary measurements and tests of things like general relativity and other really cosmology, Big Bang theory, all of these amazing things that every time we sort of dream up a new way to test and make measurements, it seems like it's working out. It's all good. And that's very reassuring. And maybe we should just take from this actually a little bit more of that reassurance that actually when we put together the standard model, for all its flaws, which numerous and
which are many, yes,
have many astronomical implications. But, you know, hey, it's how we describe the world around us. Everything from as we've said, when you're falling over and hitting your nose on the ground, to the weird and wonderful world of quantum mechanics, which we're now building some of the world's best computers with this theory, right? With quantum computing. So we need this stuff to be correct.
Yeah, we need it to work at a really, really high level, which it does, and so that's good. And I think you're actually fundamentally right, but I think the disappointment, or maybe disappointment's the wrong word. I think there are a lot of scientists out there who are champing at the bit to be set loose on a big new problem where they've actually got some experimental data to compare against. You've got a lot of people who are working on an enormous amount of theoretical physics, but they need a rudder. They need, something that they can get their fingernails into to help them find their way. And this promised to be a little bit of that if it was real. If it's not real, then it's okay. We're back to where we were a couple of months ago, which was, let's just keep working away at it, plug away at it. Let's be cleverer with our experiments and with our theories and see what we can come up with. I don't know. Time will tell.
Well, for me, if history's taught us anything, that the experiments and the data that have come out with the weirdest things that we've had to sort of really shift our paradigms of thinking of in physics, the vast majority of those have come out of very ordinary, very mundane kind of work. And they just came out of nowhere and just blew everyone out of the water. So in some ways, I think that's probably going to happen again. And the beauty of it is you just never know. It might be the next sort of very just general, ordinary step in our development of CERN. It might be the next space telescope that we send up that was looking for something completely different. And suddenly, hey, here's this new area of physics that we need to turn around and look at. That's what I find so exciting, is you never really quite know what's around that next corner.
That pretty much brings us to the end of this particle-tastic edition of the Syzygy podcast. We normally don't go in for the really, really, really small in quite so much detail, Emily, but this time we've really gone to the very nerdy centres of my brain, at least. I've quite enjoyed this discussion. How about you?
I've loved it. I had to dust off a few of my textbooks. I have to admit, particle physics is not something I think about on an everyday basis, but it's good to be reminded of these things.
Well, indeed. And look, I'm quite prepared to admit that I was making up half of the stuff that I was talking about, because it's a very, very long time ago that I was studying these things. So, listener, if you're out there thinking, Chris just said a whole bunch of stuff that is absolute nonsense, and you want to call in, want to write in to correct us, or just send us a hello, make a comment, ask a question, suggest a topic for a future show, you can do that. There's loads of different ways that you can do that. Emily, you've been away for a while. Have you forgotten all the different ways that people could get in contact with us? Here's a question for you. Name one.
You can tweet at us.
Yes.
At us.
You still remember. Fantastic. You can at us at where?
We are at SyzygyPod. That's SYZYGYPOD.
That's true. But here's the next question. Where else are we at SyzygyPod other than Twitter?
We are at SyzygyPod on Instagram, on Facebook. Just you throw in a SyzygyPod into the searchy thingy and you find us. We're there.
We're out there somewhere. Yeah. And I think it's probably fair to say we haven't used. I don't know. Have you been Instagramming much lately?
I'm still not entirely sure what Instagram is. I'm going to just
we should
admit
get
to
back
that.
on that particular horse. But we are out there and you can reach us through it. But of course, the other thing you can do is just go to our lovely webpage, syzygy.fm, where you can find all the past episodes, show notes, pretty pictures, and us nattering away about everything from particle physics to the grandest scales of the universe. So you can do that. You can go to the contact page on the website and send us a message and say hi. If you are interested in supporting the show, there's a whole bunch of ways that you can do that. You can tell everyone that you know that there's this fabulous show where they witter on about scientific stuff for hours on end. Tell the people in your life who you think would get a kick out of that, because the more listeners we got, the more excited we get, the more incentive we've got to talk about nonsense for hours on end. The other thing that you can do is leave us a review or a bunch of stars on your podcast app of choice. That helps us to rise up through the noise, and more people can find us when they go to search for interesting things to listen to. And finally, you can become a financial member of the show. You can go to patreon.com/syzygypod, where you can become a patron of the show for just $1, a quid, a couple of bucks, a couple of quid a month is enough for us to keep the electrons flowing through our website and support what we do when this world eventually opens back up again and we get to do stuff like festivals and live shows, the fun stuff that we really enjoy doing. We've got one of those coming up, haven't we, Emily?
We have, and the Festival of Ideas.
Yeah, it's here in York.
Online.
In June or July. Coming up anyway. We'll give you all the deets on the website. But I'm really looking forward to doing all of that sort of stuff again. And thank you to all of our patrons who have supported the show thus so far. You're over there on our website on the great wall of gratitude. So thank you to everyone who helps us to do what we do. We should probably wrap it up there. So Emily, we'll get back on this recording horse and ride off into the sunset of our podcast, stretching the analogy way too far. But we'll do this again. What do you reckon, in a week or two? See if we can get back into a regular schedule.
Yeah, let's do it.
Yeah, sounds good to me. All right. Well, until then, everyone, stay safe, stay warm, and we'll catch you again in a couple of weeks. See you later, Emily.
See you later.
Bye.
Can I suggest, if nothing else that we learn from this particular experiment, we definitely need to go with more the scientific drama of having the secret number in the envelope that gets opened.
Absolutely. I think that's just got to be the way. Even for something where the stakes aren't that high, I think that should totally be the norm. Like, why wouldn't you do that?
I'm definitely going to suggest it at the next conference. Let's just do it.
Yeah, I mean, it's got scientific ethics all over it, but then it's also got the X factor. It's so exciting. What are our results? Open it up, pop the champagne. Woohoo.
It's like a gender reveal party.
Just don't start setting off explosives, please, God. Don't kill anyone with your results. This is not where we want to go. Wasn't there one the other day where they set off so many explosives it triggered an earth tremor or something? Just, oh God.
I was just thinking of the run-of-the-mill ones where you just open an envelope. But, you had to take it that extra level.
But then you'll get scientists getting silly, and they'll start, do a results reveal by, focusing the beam of the Large Hadron Collider on a balloon or something, and it'll all go horribly wrong. Let's not tempt fate.
But maybe that's where the mini black holes are going to come from that we're going to use to understand the rest of the universe. Got a very loud helicopter coming over at the moment. Oh my God, it's Ingenuity coming to get us. Something's gone really, really wrong if that's happened. Yeah, I think so. And if it sounds that loud, I mean, I know it's got a big rotor, but it's not that big. All the kids outside are going nuts.